Hi everyone, hope all of you can hear me. So let me present my screen. Is my screen visible to you guys? Yeah. Okay, you guys can unmute in between when I ask because I don't have to go back to the main screen to see the thumbs. Can you see the slide? Hello. Okay, fine. So today we'll be doing like we'll be just going through the very basics of what's reverse engineering. So today we won't be going into any application part of it. It's just some basic theory which maybe some of you might have already known. And yeah, so the second part of the session will be more focused on practical applications and like using different tools for doing reverse engineering. So that will be probably sometime this week. If everything goes good, probably day after tomorrow. So yeah, let's get into basics of reverse engineering. So first of all, can someone tell me what they understand by reverse engineering? Hello, should I assume that I'm not audible? Mm, yeah, sort of. Then how would you do it? Uh, if someone knows. Okay, fine. Yeah, okay. Okay, we'll get into that. So basically, yeah, like he told, it is to figure out, yeah, let's go. Yeah, so basically, reverse engineering is to, per se, like, identify what a program does. So, yeah, it is the process of analyzing how's the behavior of a program, like how would it respond to whatever you do with it, kind of things. So this is like a very important thing in the field of cybersecurity because we need to understand, if suppose we have some malware, we need to understand like how it behaves so that we can do preventive measures against it, kind of stuff. Okay, so let me go through this. Yeah, it is a process of analyzing what a compile binary does. So compile binary is basically the program, and yeah. So how would you go about doing this? The most trivial thing will be to uh, run the binary or like run the program and see what it does. If it kind of takes inputs, you try out different inputs. So if I tell it in terminology, then this is something called dynamic analysis, where you're interacting with a program and trying to figure out what it does. And then comes the static part of it. So static analysis is simply uh, trying to like get back how the program was built, like what was the code which went into getting this program, getting this binary. So this can be done like in two ways. Like two ways means okay, one way and then you go again in depth into it. So the basic would be to do something called disassembling it. So trying to get the assembly language which then got into which then was converted into the binary. And then further, if you want to do, you can do something called decompiling and get the source code which was responsible for the assembly itself. So basically you get the code in in any of the coding languages, like C or C++, anything. Yeah. Okay. So before we go into reverse engineering, there's this other term called patching. So have you heard of patching? Yeah. So can you tell me how it's similar or different to reverse engineering, or are they even connected? Okay. Yeah. That's basically it. So the main thing of reverse engineering is to get back the code which was compiled to the program and just go through it and see what it does. So there we won't be interested in changing the code or like doing some modification for it or anything. But then patching is where we do that. So where patching is done, like for if I give you an example, so if you want to like change the behavior of a binary to uh, okay, I'll give you the example later. So basically in patching you change the code after you get the source code of the binary. So it can be like even changing one instruction in the assembly code. So you might have heard of this modded APKs and stuff. So what they basically do is they take the original one and then they reverse engineer the code. Then they patch it with their own code so that you get the desired changed binary. And yeah, this can also be used to like test stuff regarding the binary, make it more secure, kind of all those things. Yeah, so patching refers to altering a binary without having its source code. So basically, you reverse engineer to get the source code and you do the change in code. And yeah, you can also do it from assembly itself, changing specific instructions. Okay. So yeah, before we go into the technical part of it, I'll give you one example of uh, where a reverse engineering thing was applied. This is a very kind of basic example. So you guys might have already heard of, like most of you might have heard of this WannaCry ransomware, which affected a lot of Windows machines in 2017. So what it basically did was the in the affected systems it basically encrypted all the files and you had to pay some money to get it unlocked. And this happened because so yeah, and this was one of the ransomwares which spread like crazy during that time. And that thing was because so in the same year there was this leak. So NSA, the National Security Agency, the their hacking tools were leaked by this. I think the organization name was some Shadow Brokers or something. They leaked all of this. It's due to some political reasons or somewhat. And one of the tools in those in that leak was this thing called Eternal Blue, and this tool was used to exploit this protocol on Windows, which was responsible for spreading this uh, ransomware very fast. So anyway, going to yeah. So after this thing, the ransomware started spreading. Many cybersecurity researchers were called upon, and they were assigned to like mitigate against it. So there was this cybersecurity researcher. His name was Marcus. So he reverse engineered the ransomware, and he found out that in its source code there was a URL which which was embedded in the source code, which basically tried to connect to this domain. And if it was not, the intended way was it should not connect. And yeah, that's how the ransomware kind of operated. I'm not going to too much details here. So what he did was he basically bought the domain and like registered it. Now the ransomware it was able to connect and it halted the continuation of the spreading. So basically, he found out that URL and he realized that it played an important role. But anyways, yeah, then there were like later versions of WannaCry which didn't use this, and yeah, it continued to affect. But then this was a major like um, major defense which came up temporarily against the thing. Yeah. Okay, so now talking about compilation. So compilation is the process of converting human readable source code. So whatever code you write in any of the high level languages like C or C++ or anything, it is then translated into machine code or binary which the computer can understand and the processor can process. So this compilation, although say it in one word, it includes some some stages or like sub processes kind of thing. So these are pre-processing, compilation, assembly, and linking. So what are they? So pre-processing is, so in this high level languages you might have done some imports, you might have imported a library, you might have given macros. So what are macros? Macros are like some kind of, you can define things. So for example, if you what can you say, like if you want a shortcut for a for loop which like runs through like these many integers or something like that, you can just make like a macro which does that thing and you can use it in your code anywhere. So in this pre-processing, what the compiler does, okay, this compilation is done by the compiler, which is a program, and the compiler, what it does is it will include all the header files. So if you have used another in as the header file is basically, it's another program which you want to include. So if you have a function which you want to use from another program, so then you will import those as header files. So it'll expand all that code, it'll import that header file completely, and it'll expand all the macros, and it'll remove the comments which is unnecessary for the compiler. And now the main part of the core compilation is happening, and there is where it will convert it to assembly. It'll generate the instructions for it, and after that the assembler, what it does is it converts this assembly code into into the machine code, basically the binary, and this outputs a file called the object file, and there can be multiple object files also. So but this object file is not yet ready to run as a program, and if you have used some external libraries or anything like that, now these libraries are like kind of huge, so you don't want to like completely take in the library or anything. So what the compiler does is it just links the library to your program, so you will be able to use the functionalities of the library. And the linker, it links the object files and the libraries, and to make the final executable. So all, if there are multiple object files, all these are like clubbed together to make a final executable, and yeah, that's what you run as a program. Okay, yeah. So now talking about, now we just saw that how a binary is made, but then our main goal here is to reverse engineer this binary, so to get the source code of the binary. So we'll go into the first step that we could do. So that is disassembly. So the hierarchy is like the source code first goes into the assembly, it's converted to the assembly code, and now the assembly code is converted into the binary code. What disassembly does is, in disassembly will convert this machine code back to the assembly code. So this is done by something called a disassembler, and that's also a program. So a disassembler will take the binary code and convert it to the text representation. So assembly, so binary code, it's just binary, that is ones and zeros. This can be understood by the processor, but to us it's basically a lot of ones and zeros, and there's a lots of ones and zeros, and so it's converted into assembly. So in assembly we'll have, at least we'll have some textual information, so we'll be able to see the instructions, the whatever names of the instructions are there, which the binary uses, we'll be able to see that. And one to one conversion, so one instruction will be one line of text in the assembly code. So how does a disassembler work? First the binary is loaded, and now the bytes are read sequentially. Okay, and it depends on the architecture also. And it chooses between linear swap or recursive descent. So I have just put these terms here so that maybe you can go later. I have referenced this link here, which is like a very good article or like resource which you can read about this. Basically, linear swap or recursive descent are like the techniques which are used to like identify the instructions. So if in linear sweep, basically it goes through it in a linear fashion, and in recursive descent, it is more smart. What it'll do is it'll identify control flow statements like loops or function calls or whatever, and then yeah, so and it disassembles it according to that. So linear swipe might be fast, but then recursive descent will all have these all features. Yeah. And now decompilation. So now we have the assembly code, and okay, for a decompiler, it need not be directly disassembly has to be done. So like yeah, I think it will do disassembly during the process. But anyways, it will take the binary code or the disassembler output and convert it to high level code. That is basically decompilation. And yeah, the this is required to validate programs. So suppose you are kind of going to install some program maybe in your Windows machine, and you wanna make sure it's the original. Like if you're downloading some program from some alternate source, and they might have done what I told you earlier. They might have done some patching on it, and the patching will like kind of exploit some vulnerability in your computer or like compromise your machine. So what this so for cyber security, for like this software security, what they'll do is they'll decompile it and see if this is having any faults or like if this is vulnerable to anything or sorts of things. Yeah. Okay, now CPU architectures. I mentioned earlier some disassembler, it'll do the disassembly based on the CPU architectures also. So what is architecture? Architecture is like basically how you'll build stuff, like building of something. So CPU architecture means how the CPU is built in the software sense. So it defines the design and structure of a processor. So what kind of instruction set it uses, about the registers, and how it processes. So there are two main classifications of the CPU architectures, which is CISC and RISC. So CISC is complex instruction set computing, and RISC is reduced instruction set computing. So in CISC, it uses complex variable length instructions. So what this means is it might have an instruction like you multiply something and then push it to this register, push the value to the register. So it does like kind of a combination of two things. Yeah, and yeah, for decoding this, there is on the hardware part, there are more transistors will be used. The example of this is x86 architecture. And RISC, it uses fixed length instructions, and it is very it's kind of very simple, and it's easily less amount of transistors are used to process it. An example of this is ARM. Yeah. Okay, so there's this small diversion I would like to take. It's like I'll just say what computer organization is also, because like when you talk about architecture, that also comes to play. It's nothing. It's basically if computer architecture like defines like or says how what a system does, organization will take care of how it does. So suppose you want to do addition, hmm, you want to do an add instruction. So in the kind of hardware level, how will this addition be performed? So there are things like adders to do addition. So it'll say how it'll do those tasks. Yeah. Okay, now the basic x86 assembly. Anyone has any doubt till now? I think I'm going a bit too fast because there's not a lot of material, and yeah, this is all you need kind of to understand. Any doubts till now? Yeah, you can also share your doubts in the group, or yeah, DM, or yeah, anything. You can clear it later also. And yeah, so now some of the assembly instructions. So I said that assembly will be in text. So these are kind of the textual representation of few instructions, like what they'll do. So there are these data movement instructions which will, so I think you had this binary session where, yeah, I think Isfarul told about stack and everything. So stack operations. So this move instruction, what it does is it will move data with from the registers to the stack, or like between registers and all this, and push will push a value to the stack, and pop will pop, like remove the topmost element of the stack. And there are a few arithmetic instructions. I think it's kind of self-explanatory, you can just go through the slides later. It's just performing basic arithmetic operations. And yeah, control flow instructions where it'll do the assembly will correspond to loops, and then function calls returning from the functions, and subroutines and everything like that. Yeah, now there are these two types of binaries. I'm just mentioning it. So there are these two main types, which is ELF and EXE. So ELF is basically the binaries in Linux systems, or like Mac, which is a Unix system. And yeah, it does not have any specific extension. Whatever you get after compiling a C code, basically, it will be the a.out file is basically an ELF binary. And there is this Windows executable, which is exe. It has an exe extension, and you can just simply run it by double clicking or whatever. Yeah, now I'll just show you these tools. I'll link, I'll put links for installation of them. And if you have any trouble installing them, just DM or put in the group. And yeah, I'll resolve that. I'm not showing the installation right here because like all of you will have different kinds of uh, operating systems, and it might vary. So for Arch and all, it's very easy to install using Pacman, but then in others you'll have to install Java separately and do whatever. Yeah, so I'll show you Ghidra, and basically to run Ghidra, you just you run the command Ghidra and it'll run Ghidra. So Ghidra is a tool developed by same NSA only, and it was made open source. So yeah, I'll create one binary. I'll create what is it? Test. Yeah. Oh, okay. Did I put it in the group? Mm, fine. Yeah. Yeah. Now we'll compile this C code. Yeah, and we have this a.out. So how will you use Ghidra is first you'll go here, you'll create a new project, and yeah, project name whatever, rev session, and now you select this and you import a file. Where is import? Yeah, import file and select it. Yeah. Select the binary, click on OK. Yeah. and it'll ask you if you want to analyze it. You just click on yes, and like go with the default options. Now, in the left side, you can see that there is this program tree which will have various parts of the binary, and you don't need to care about that. And there is a symbol tree. I think you can see it. Can't zoom in. Yeah, there's a symbol tree which will have the functions of the binary. So here you can see there's a main function here, and if you click on that, on the right side you can see the decompile code. In the middle you will have the assembly, which will have this instructions like push RBP, move RBP. This is the main function, and here is where it will do. Wait, yeah, we returned this. We multiplied it by 2 and returned it. So the multiplication is done here. And yeah, so here you can see this is the decompiled code, and we can see that there is no definition of that variable, or nor there is this multiplication by 2. So why this happened is basically the compiler is a very smart thing. It'll like simplify everything what your program does, and it'll optimize a lot. So here it understood that that variable, it was only used once, and it didn't require any other things, so it directly took the value 2 after multiplying it. So we see it like this here. Yeah, that's basically decompiling, and you will for complex binaries you will see a lot of functions. I think in the next session you will see more detail into it, and I'll show you one more tool. Maybe not everyone has knowledge about it, but you may see it. So basically, you see, this is Ghidra. I know it looks very bad. See, it is written, the full UI is Java based, and like there's no other kind of, like no one has changed, like made an alternative in some other language. So Java, you have to bear with the looks. It's very powerful, but it looks so bad, and it's very hard to navigate also. Yeah. So the other tool, so kind of to make the feel better, there's this tool called Cutter. So you can go to this website, and you can download the app image. So there's something called app image, and you can just run it without even installing it. So it's basically you'll get it as a kind of direct executable. So I have it here. So what I'll do is I have renamed the app image to Cutter. Wait, it's not here. Okay, and I'll give it my binary, and I'll click on OK. It'll analyze it for me, and now you see the UI looks much better. And yeah, you can, there are these sections here. So this will give the strings in the binary, imports, and here you will see the assembly code. It looks so nice compared to this thing. Yeah, and yeah, this was the main thing I was about to say. There's this feature called graph, and it'll show you exactly like how the program will flow. So suppose you have an instruction here which will compare some value, and it will do something for one comparison and the other thing for other comparison. This will come as a graph. Here the program is very simple, that's why it's not there. But you can later try out some program with like loops and things. So to get like and you can run it in Cutter to get a very nice graph view. And of course there is this decompiler, and the decompiler used by Cutter is Ghidra. So it uses the Ghidra decompiler, and but here we can see that there are something. Wait, what? Yeah, main function. My bad. Main function So here we can see that there's this small kind of variable declaration kind of thing. So suppose you had a lot of these in your program. If you run it in Ghidra, it will realize that it's all useless and it will just show you the code which you will actually like want to see. That's the only kind of difference. But here you will see this also, and the UI looks much better. That is Cutter. Yeah, I think that's it. Yeah. So I'll put some reference links for you guys to read also. I'll put like the installation links of like the guides of Ghidra and Cutter, and yeah, I might also put some more links regarding these topics. And yeah, that's it. So hope it was clear. This is kind of a pretty short session because it was just supposed to be introducing you guys to what is reverse engineering, and all the like using all these tools extensively will be done next session. I think it will be taken by Achintya, and yeah, the try to install this, like use any of these, install Ghidra or like learn to run Cutter, and if you have any problems regarding that, you can let me know or just let anyone know, and we'll help you out with it. And any doubts so far, like regarding the session or anything that I explained? I think all these are like very simple to understand. Just we are not going in depth to any of the how it works, like how kind of a decompiler works or anything. Because our main aim is to get the source code and understand what it does. Yeah, any doubts, guys? No. Okay, hope it was fine. I'll stop recording.